My name is Eli Reches. I introduced myself in the morning. And I have the pleasure of opening the second session of our conference on water in Israel and the Middle East, regional water sustainability and resilience. The first speaker in the second session is Naphtali Lazarevich. Now, you think Lazarovitch is an Ashkenazi name, which is true, but this morning I learned that there is another half, which is not exactly Lazarovitch, but rather an Iranian name. You didn't tell me what it was. Avrahami. Okay, so Naphtali Lazarevich Avrahami, if I may say so, is our first speaker. He made all the way from Ben-Gurion University. He's an associate professor at the Wyler Department for Dryland Agriculture, Jacob Blaustein Institute for Desert Research, Ben-Gurion University. His main research interests are creating a better understanding of water flow and solute transport. By the way, you realize that I don't understand the word from what I'm reading. I told you I come from humanities, but he will explain. Increasing agricultural water use, efficiency, and so forth and so forth. I will not take his time. Ladies and gentlemen, join me in welcoming Naftali Lazarevich.
So my objective in research is to understand, as you said before, water flow and solute transport in the soil, plant, atmosphere continuum in order to increase agricultural productivity. But in the same time, we have the environment there, and we want to maintain the environmental sustainable. So we don't want to pollute the environment with our agricultural activity. So we have the root zone. This is the root zone when we have roots. And this root zone is very important for us because we grow plants inside, and this root zone is supporting the plants. We have the plant, and water is flowing from the root zone into the stem, into the leaf, and then from small opening in the leaves, the stomata, water evaporates to the atmosphere. In the same time, the plant is uptaking carbon dioxide from the atmosphere. This is a nice factory producing sugars and minerals from the soils together with the carbon dioxide creating the plant. Okay, we have several fluxes in the root zone. Some of them we can pray and they come. Some of them we can pray and they will not come. For instance, rain. This is something that we don't have so much. In Israel, where I live, we have 80 millimeters per year. So this is the amount of water that we get annually. It's not a lot of water. And this amount of water cannot support the transpiration to produce good plants, healthier plants, and plants that produce enough food. Therefore, we supply irrigation. Irrigation is mandatory. We supply irrigation, and this will be my talk, how we do it, when we do it, and how much we bring into the soil. We have other fluxes that are not productive fluxes, like soil evaporation, water that evaporates from the soil surface, and this is not productive process, and we want to minimize it. Other fluxes like deep percolation is water that leaving the root zone from the bottom part. It's not only water, it's also nutrients that are leaving the root zone, and they can contaminate the groundwater, also other agrochemicals, pesticides, herbicides. So we want to reduce also the deep percolation. Okay. How to do it? In Israel, 70% of the irrigated fields are drip irrigated. It's a huge number. And United States, just to compare, it's 7%, which is a big chance to increase it, but still it's 7%. Sprinkler irrigation is 30%, and United States it's 48%, and surface irrigation in Israel is 0. No surface irrigation. You cannot see surface irrigated fields. We cannot afford it. We don't have enough water. We don't want to contaminate the groundwater with the leachate, so you cannot see surface irrigation in Israel. So mainly you will see drip irrigation. Okay, when to irrigate and how much to irrigate, those are very serious questions. From the same amount of water, you can produce different amount of yields. The current estimation, the worldwide, the average number, not in Israel, but the average number, that 60% of the water is not used by plants. Okay, so if you take a cake, 40% you eat and 60% you throw. You throw it to evaporation, as I mentioned before, soil evaporation, drainage below the system, runoff from the soil, and leakage in the system. This is a big issue, leakage in systems. Our challenge is to produce as much as food, fiber, and biofuel as possible, and using and affecting as little water as possible. We want more crop per drop of water. We don't have enough water. Yoram mentioned before that the water is very expensive. We produce it, we bring it to the field. Now we want to use it efficiently. We want to prevent fluxes that are not productive. We want to increase the fluxes that are productive. So how would we do it? In my lab, I have several options to increase water use efficiency, and I'll show you what are the tools that I'm using in order to do it. One of them is using lysimeters. Lysimeters are containers, similar as you grow plants in your home. In a container, we have plant inside, and we just do water balance in this container, the same water balance that you do in your bank account. You have every month your salary. This is the irrigation. You have the drainage. This is the saving account. And you have your balance. This is the storage in the container. We have scales that measure the balance. And this carousel have 24 containers that each one of them is located on scale and continuously measuring the storage in the container, continually measure the irrigation and the drainage. So we have those in a big container with date palms and sweet basil and other containers that doesn't have scales. Sensors. We have many sensors. Some of them we buy and we test, like those water content and salinity sensors. And some of them we produce by ourselves, like this subflow meter that I will mention later in the talk, or this root camera that we install it through a mini rhizotron, through a transparent pipe into the soil, and we take picture of the root and we see the development of the roots. Or we use those controllers, those inexpensive Arduino controllers to generate wireless sensors network in order to get the data from the field into the decision support system, which will be located always near the user. And all this data is coming to the computer, and then we can compare this data with numerical models that simulate the scenario, simulate the water flow from the drip irrigation line. Here it is, the drip irrigation line. This is the water coming out into the roots and then to the plant. Of course, this is just a model, and always we want to calibrate the model and validate the model, but in the end, we want to eat fruits and not pixels, so we need to go also to the field and do those experiments, and I will show you several experiments that we are doing, and how we are using those models, how we are using those sensors, how we are using those lysimeters in real field conditions in order to save water, in order to minimize the non-productive water fluxes. Okay, the first story is about bell peppers. We are growing bell peppers in net houses in the Arava Desert. And the water is pretty saline. And we use those lysimeters also to take the laboratory and to bring it into the field, and then we can measure fluxes. So here is the story. We have water shortage. We mentioned it before. The water are brackish in this area. So this area is not connected to the national carrier, so we are not connected to the desalination that Yoram mentioned before. And all the water is coming from the groundwater, the local groundwater, which is saline. The soil is really heterogeneous. I will show you a picture, and stony soil. And there is extreme summer there. Temperature during the day can be 43, 45 degrees. Night temperature, it's really high. For plant, it's really hard to grow in such environment. We need to supply irrigation. Solar radiation is high, relative humidity is low. the pan evaporation, if you leave pan with water of 2.5 meters, after 1 year, you will have no water there. The rain, almost we don't count in millimeters, we count drops. We try to find the drops when it's falling. This is the soil that we have there, really bad soil. It's really hard to do agriculture in soil, even if you use drip irrigation. What the local farmers are doing in this region is taking sand from the sand dunes that are nearby and covering the soil with 0.5 meter of soil. Now the environmental agency would not allow it anymore, and we need to find a new solution. So 5 years ago, one of my PhD students came to me and suggested an idea, is to use a capillary barrier. It's a trench that we dig inside the soil. In the bottom part of the trench, we put gravel, and we put some material inside in order to be able to grow roots. We have drip irrigation on top, and we can grow plant. What is capillary barrier and why we're using it? We want to increase the water content, the amount of water in the root zone. We want to reduce the spatial variability. You saw the heterogeneous soil. It's not good in agriculture. And we want to protect the root zone from capillary rise, from water that's coming from below, from the saline aquifer. What is a capillary barrier? A barrier, you know what is a barrier. So if you take plastic and you pour water, water will not penetrate this plastic. This is a barrier. But what is a capillary barrier? It's as a physical state when you take a soil, like clay soil, with very, very small particles, with very small pores, and you put it on top of soil with very big particles and very big pores. In the middle, you create a capillary barrier. Water flow will go from the clay and stop here in the capillary barrier until it will be saturated. Only when it will be saturated, water will flow down. We use it for this capillary barrier in landfills to cover and divert the water infiltrating from rain. This is rain that's coming to this capillary barrier, and we're diverting the water, and we don't want that this water will go inside the sensitive underground. Let's say that we have something that we want to put there for many years, and we don't want the water will come through. We make this capillary barrier. So, when I have an idea, the first thing to do is to go to the model and test it there. Is it going to work? Is not? Let's see what is the best, and let's try to optimize what should be the depth, what should be the size. And to do those experiments today, it's very expensive. Therefore, we go and do it with models. So this is the model, Hydros 2D, 3D. And this is 100 centimeters wide and depth. And yellow is dry. And I'm starting the irrigation in the computer, not in reality, yes? But we're also testing it in reality sometimes to compare between them. But it's easier in the model because it's not consuming time as in the field, and there's air conditioning in the room. Yeah. Okay, so after 1 hour, everything the same. And after 48 hours, you will see this capillary barrier is holding the water, and it's holding the drainage, but it's not a barrier. So water will continue to flow. If we will continue to irrigate, water will continue to flow. However, the water content here in the capillary barrier will still going to be higher than the control system. So we implement this capillary barrier in field conditions. So you see in those pots, in those containers, we have this capillary barrier. Also here in the field, growing bell pepper. And let's see some results, if it's beneficial to the plant or not. So this is fruit yield, kilogram per meter square. How many kilograms we get in 1 season of bell peppers? In this capillary barrier, we get approximately 11 kilograms per square meter. And without the capillary barrier, we get much less. So we increase the yield by using this capillary barrier. So that was the first experiment. And always, when you have the first experiment and it's working, you want to do more and more experiments. The second experiment that we did, remember, we have saline water in this region. And when you have saline water, you want to irrigate more than the demand of the plant because you want to leach salts. Otherwise, you will accumulate salt in the root zone, and the plant will suffer from high salinity. So we are irrigating in a ratio higher than the evapotranspiration. So 1 is just to give the amount that the plant needs, and 2 is twice than what the plant needs. So half of it will go to drainage, which is not good for the plant. Yes, it's going out. Anyway, with the capillary barrier, always we got higher yield than the control. The difference was only with and without the gravel layer. This is the difference between the control and the capillary barrier. So it was a success, and farmers started to use it. And this is the first farmer that started to use this capillary barrier. He used it for other reasons, even a reason that we haven't thought about. So farmers did experiments while we are doing our experiments. So the reason that this guy used it is to prevent the capillary rise from the subsurface underground water. So here in the middle, you see very high salinity. So water evaporates from the soil, the salt stays behind and accumulate there and accumulate, and then it can be not good for the plant. And here, when we have the capillary barrier, the situation is much better with much lower salinity. So farmers in this area are using this capillary barrier. They're making a trench, they put in gravel, they put the drip irrigation, and they are growing bell peppers, and everybody is happy. They can export it to Europe during the winter, when in Europe they don't have enough good favorable conditions, and they have favorable conditions in the desert. So this innovation or this development came to reduce the amount of drainage below the root zone. One other innovation to prevent soil evaporation came from Yaakov Katan. Another innovation, the drip irrigation innovation, came from Simcha Blas. The cherry tomato with the long shelf life and manipulated plants came from Nachum Kedar. And all those innovations came from the Negev. So as Ben-Gurion said, it is in the Negev that the creativity and pioneer vigor of Israel shall be tested. And there are many innovations going on there, and this is one of them. I don't know if it will be famous as the drip irrigation, probably not, but it's there and people can use it. This is the reference if you want to read more about the capillary barrier. The next story is about date palms. Date palm is a very important plant in Israel. We have more date palms in Israel than people. Yeah. One fruit costs $0.25. If you don't believe me, next time that you go to the market, count fruits and see how much it costs you, and you will see that is quarter. So the farmers call it the tree of quarters. So they look up and they see many quarters there in the sky. This tree is a very nice tree. It's a monocot tree, and we can grow it also in those big containers to make the water flow and solute transport balances. And what is nice that came from this experiment, that we have a stamp, from the Israeli Stamp Authority of 2.5 shekels, so you can buy this stamp. But anyway, in this tree, it's very hard to measure in the canopy because it's a very tall tree. And for scientists to go up, it's dangerous, and the students would not like to climb there because it's hard. So we thought to do a sensor, to produce a sensor that will measure the subflow, how much transpiration, how much water is flowing in this pipe. This is a big pipe, and water is flowing there. In the morning, when the stomata are open, water is leaving into the atmosphere and evaporating, and there's a lot of flux going on there. One tree can consume 1 cubic meter a day. One tree. And if you have 365 days, it's a lot of water, only for one tree, and then you can calculate how much you lose for one fruit. Yeah, it's a lot of water. So when you're eating fruits, you're actually eating water. Yeah. Anyway, the sensor that we made is putting an electrode into the stem and producing constant heat. With this constant heat, we can measure the temperature nearby the sensor. And we can measure the ambient temperature of the stem in a separate place and have the difference between the ambient and the heated place. Now, during the nighttime, when there's no transpiration stream, the difference is really big because one is heated and one is not heated. But during the day when water is flowing there, the delta, the difference between them is decreasing. Therefore, we can calculate and compare it to the lysimeter, and this is what we did. So during the nighttime, nothing is going on, and suddenly 6 o'clock in the morning, transpiration is going up. This is midday, and then it's decreasing because the sun is falling down, and we have less demand from the atmosphere. So the comparison went good, and we took it out to the field, and we put it in real trees, and the reduction, after we closed the irrigation, there was a reduction in flow. Yeah, and then we said, okay, this sensor is working for us. Now the next step is to use it in a big experiments, and that's what we are doing now. Okay, this is the results of the experiments that we have now. We put it in several heights in the tree. One is closer to the canopy and one is closer to the earth. And we see differences along the day. The one that is higher is here, 10 meters, and the one that is lower is in 2 meters. And we see differences between them. So the differences are coming because of the capacity of the tree. Water is leaving to the atmosphere, but new water is not coming because the soil is limiting the flow. And during the nighttime, there is recharge of water. So all this we could learn only because of sensors that we are putting inside the tree and measuring continuously the water consumption of the tree. Another sensor that we developed, we wanted to measure the frond, the first leaf of the date palm. This frond is growing 5 centimeters a day, between 3 to 5. And people are measuring for many, many years this frond elongation, but they didn't realize that most of the growth was at night because they didn't do continuous measurement. So we did continuous measurement. So there is a swivel here that there is a rope that is connected with a screw to the frond, and whenever the frond is going up 90 degrees, we have pulses in this flow meter. Okay, this is the results that we are getting. So this is millimeters, and this is the elongation. So you see that during the nighttime, from midnight to 6 o'clock, there is growth, and during the daytime, there is almost no growth. To have growth in plant, you need turgor. So if the stomata are open, water is leaving into the atmosphere, and the turgor is decreasing, and therefore the plant cannot grow anymore. And during the nighttime, when there is more turgor, the plant can regrow. Now we did an experiment to test it. We took all the flowers, so prevent the plant from having flowers and then fruits. So 0 has no fruits, and 100% is all the fruits are there. So all the fruits are there, the plant is doing a lot of photosynthesis, and the stomata are really open, and a lot of water is coming out. And in the other one, the plant is more relaxed. It doesn't need to do more photosynthesis, and it can grow himself with growing the leaves. So there is a big difference between those two. We tested it for a long season. Here you see the growth rate, centimeters per day. So you see, in the beginning of the season, there are almost no difference between, or statistical difference between the two, the one that have or not have. But later on during the season, the one that have a lot of fruits growing very slowly compared to the one that have many, many fruits. Now we took this idea, and farmers are now irrigating differently their crops based on the amount of crop that are living on the tree. Because this is a majule variety, and they want big fruits, so they will harvest most of the yield, and they will reduce the amount of yield. So if they are reducing the amount of yield, they can reduce the amount of water also. So everything in the end connected to water. Okay, some references here. The last story that I will tell you is about desert viticulture. We like to drink wine. and we have very nice conditions to produce wine. This is the desert area, and in the valleys we can grow vines. The weather conditions are perfect for wine in our region. Nighttime temperature is below 20 during the summer, and during the day it's pretty hot with high radiation, produce a lot of sugar and can have a lot of stress. When the plant has a lot of stress, there is a lot of sugar inside the berries. Wind speed, we get every day a sea breeze, and we have some cooling down the atmosphere during the afternoon. So it's getting to 20 degrees. So it's quite nice weather during the summer. Now, everybody wants to grow vineyards now, and they grow it with regular water, with tap water. This is the water that is available in this region, and we want to conserve. Part of the water is living from soil evaporation from the soil surface. This is, again, non-productive flux. We want to prevent it. And the idea in this research was we wanted to quantify this amount. How much is going out from soil evaporation? So if you cover and put mulch, you change the whole situation and you cannot really investigate it. So we decided to go with different ideas, and we put microlysimeters there to calculate or to estimate the fluxes. So this is one day of pictures in July in the vineyard. You see that during the daytime, the shade is also moving. So when there is a shade on top of the soil cools down and the demand is also decreasing. Why it's important? Look at the temperature when we have infrared images. Here in the middle, it can be 60 degrees, really hot. You can barely put your foot there. Yeah? Here, when it's evaporating water, it's 25 degrees. It's cooler. When water is evaporating, the soil is, you need energy for the evaporation, and the soil is getting cooler. This 30 degrees is just from the shade that we have. So with all this, we could calculate with models and with some campaigns that we did. We calculate that the evaporation out of the entire irrigation is 10%, about 10%. So 10%, sometimes it's a lot, but for this situation, for this crop and in this region was not enough to put some mulching, and usually the farmers are not putting mulch because the soil evaporation of 10% is not enough, and they are not saving money by this. However, they can increase the size of their field by 10%. So now farmers are putting mulch because of this. So they don't want to save water. They want with the same quota that they have. Yeah, remember in Israel we get a quota. A farmer gets a quota. So with the same quota, he can increase its field by 10% and make more profit. Oh, here we have some references for this work. Okay, I'm almost done. This is a great man. I live in a campus that is named after him, and he has many quotations. One of them that it's, if an expert says that it cannot be done, you can get another expert, yeah? Another great person. Yeah, both of them are really giants. 1 minute. I have two projects that are going, two big projects, two consortiums that I'm going on now in my lab. One is the root of the matter. Don't try to Google it because you will get a dentist. It's a knowledge center of 25 researchers that are investigating the root zone from different aspects, both microbial community in the soil and sensors in the soil and grafted plants that we are trying to manipulate the root zone with grafting vegetables. And we need students. We need students. So if you hear about students that want to come to Israel to do master degree or PhD on those topics of root zone, they are welcome. We have very nice scholarships for them and housing, and they are welcome to come. The second project is about viticulture. If you like to drink wine, we are always testing, in the end of the experiment, we're testing the quality of the wine. So this is a project with several countries, Spain, Italy, and France and Israel. And we are trying to optimize the water management and introduce new rootstocks and sound genotypes. Okay, those are the people that are helping me in my lab, the students, the technicians. I would like to to thank them, and this is the view from our campus that you are welcome to come and to join this very nice view. You had it also in your presentation, Yoram.
Thank you, Naftali, for an amazing presentation. Anyone who has been to this area, to the Negev, to the southern Negev, and has seen the arid land, knows and would appreciate the almost miracles that are being done through these scientific developments. My other comment is that you mentioned students coming over to the Ben-Gurion University campus. In fact, one of our students is preparing to go, right, Aaron? Soon to spend a summer internship with Sdeboker. So this is working. I open the floor for any questions, comments, remarks, protests.
Everything was clear, huh?
No. We have, yes.
Limestone? Yeah. There's chalk, limestone. There are layers, yes, like in a cake. The white that you see there is chalk. But yeah, limestone. And yeah, the pH of the soil is about 8. Yeah. So the capillary barrier that we're putting in this soil is also helping us to reduce the pH a little bit. And the pH inside the capillary barrier is 6. And then the uptake of nutrients is better. Otherwise, we have problems of iron deficiency in plants in those soils. The plants are really usually chlorotic, so they are yellow.
Shoshana?
You talked about the farmer using your research. How widespread is that use?
It's pretty amazing. The farmers in Israel are usually educated. They went to the university. Some of them went with me to university. And they went to be farmer, and I went to be researcher. And we are talking. And there are research and development centers that are transferring the data. And sometimes, and I don't like it so much, during my experiment, they will take some of my ideas and do experiments in their fields already. So they're really open to innovations, really open to cutting-edge science. Sometimes it's not good because we don't know always what we are doing, and it's research, and you never know what will happen in the end. But they're willing to take the chance. And this is really nice that we have a community that really is supporting each other to advance the research and development. Yeah.
Thank you. The mic is coming. Okay, Roti,
I have two questions, short. One, how long has this been going on, and aren't you concerned that some of these experiments can create long-term processes that will create issues for the environment rather than just maximize the efficient use of water? And the other thing, when I was talking to people in the Arava doing palms, they said that they were working a lot with the Jordanian people who were working with palms for generations, and it was very, very interesting for them to compare, because some of the common sense expertise of people working in the field for generations without those technologies actually seemed to complement very nicely the technological thing. So I wonder about the connections between, old-fashioned doing agriculture in these conditions and the impact of technology and science.
Yeah. So I start with your first question about, remind me again, it was about?
Long-term processes.
No, long-term processes, yes, it's very important. Doing agriculture, we are contaminating the groundwater, period. It's happening. Also contaminating the air. However, we want to minimize it because we do want to do agriculture because we need something to eat in the end. We want to produce our food. So we can import the food, but also the contamination will be somewhere else. So we do want to produce our food. Now, we want to minimize the contamination, and therefore we put sensors, we use models, we use those lysimeters to do long-term experiments and to see what is the quality of the drainage in terms of nutrients that are there, in terms of herbicides, pesticides, and they are there. But we want to see how much, and we want to minimize it. And by changing the management on top of the surface, you can optimize it, you can minimize what's going below. Okay? It's not 100%, it will never be 100%. The fact that we are sitting here and releasing carbon dioxide, it's a gas that it's not good for the atmosphere, but we are here. Okay? This is for the first question. The second question was about the knowledge that was gained in the Jordanian side for date palms. You see, those varieties that we are using are relatively new varieties and new techniques that we are going, and we want to produce big fruits that those are sold in higher price. Yes, we want to get the price, not only the taste, not only the quality. So quality is not only taste, it's also size. When you go to the market, when you see a big fruit, you will buy it, and you will never buy the small one. Yeah, this is public, what the public want. And we are trying to give the public what they want. And I'm dealing with irrigation. And in the Jordanian side, we come and we teach them from time to time. We have seminars between them, but usually we teach them about irrigation. Sometimes they can teach us about diseases that they have. And they have now several insects that are in their sides. And the insects still not coming to our side, even maybe the insect know that there is a border. There is a wall, no? No, there's no wall. But probably something that we are doing, preventing the insects to come. But in some places, we do see the insects coming. So hopefully, their knowledge about the insects will be valuable for us in the future. But not yet, because we don't have this problem yet. Okay.
Yes.
So I'm an electrical engineer, so I had a sensors question.
Good.
So one of the things you pointed out that you're able to measure the flow of the sap, do I understand correctly? And there's another one, if you correlate that with a temperature change between the top and the bottom. I just wanted to understand a little bit more about the sensors that you're using, and also what, if there's anything about those sensors that if they could be improved, what would you want to have to make them more useful for your studies?
So practically what we are doing, we're inserting a sensor with a constant heat. It's 200 milliwatts. It's not a lot of power, but it's a constant power. And then you measure the temperature nearby. So if you're inserting heat into the room, the temperature will increase. Yeah? And then we are measuring the temperature in a nearby place, which is not affected by this heater. This is the ambient temperature of the water inside this stem. Now you have a delta temperature between them. During the nighttime, this is heated, this is not heated, the delta is big. It could be 2, 3, 4 degrees, depends how much we heat. And then during the day, the temperature difference is decreasing because water is coming from the roots through the stem into the atmosphere. And then it's reducing this delta. By this changing during the day, we can calibrate it to water flow because we have the actual water flow from the lysimeter, the big container and scale that we have. So we can correlate between them and know exactly how much water is leaving the plant and flowing there inside this conduit. Now, we have the sensor. We want to optimize it. Yeah, I published my paper. Now I need a company that will take it further. Yes, so it's not my interest anymore as a researcher to do the optimization and to do the fine-tuning because I went to the next sensor. So if somebody is interested, yes, you can build a company based on this knowledge. It's available. And yeah, this is one of our problems. We have a good sensor or good method. What would we do with it now? Yeah? How are we going to take it further away? We need to invest money. I don't have money.
You said that agriculture contaminates groundwater as well as air. So what are those contaminants?
For air, we release greenhouse gases. Yes, carbon dioxide is released during the nighttime. Methane is in some places is released. Nitrous oxide is released. All of those are greenhouse gases that make our planet warmer, probably, because of the greenhouse effect. So agriculture is releasing gases. For the groundwater, is mainly things that are inside the water, yes, like nitrates. It's something that the plant absorbed and needed for its use. But then if it's not using all what we give, some of it will be leached down. And some diseases are because of nitrate, yes. Some pollution can be created to a water stream because of imbalance between nitrate and phosphorus, okay? So those are contaminants that coming from agriculture. Pesticides, we use pesticides. Yes, we use herbicides to reduce the herbs and pests. And if rain is coming and we have runoff from the field, those pesticides will be transported to somewhere else. Maybe they will be converted to another species, but maybe they will stay there. Maybe the another species will be more harmful for people. So that's what we do.
Thank you very much again.